Hello and welcome to Course 0 Lesson 6. Today we'll be discussing differential equations modelling, and in this lesson we'll be building on our Lesson 4 video on differential equations to discuss how we can actually solve systems of differential equations which may be difficult to solve analytically, and instead we use numerical computational solvers to arrive at our differential equation solutions. If you recall, in Lesson 4 we solved a separable first-order differential equation by hand. While we were able to solve that particular differential equation analytically by hand, that's not always possible, so often we'll use computers to help us solve these differential equations, especially in modelling when we're using a system of differential equations to describe the biological process that we're modelling. I won't go into great detail about how we've arrived at these differential equations. We'll go into more detail on that in the next lecture, but this could be considered an enzyme-catalyzed reaction, or a model describing an enzyme-catalyzed reaction. Obviously, it's a system of differential equations, you can tell. All of these have the form of a differential equation. Just to quickly go over what each of these is in the enzyme-catalyzed reaction. This first blue equation is the change in substrate over time. The second is the change in enzyme over time. The third is the change in the enzyme-substrate complex over time. And the fourth is the change in enzyme-catalyzed product over time. So, the end result of this enzyme-catalyzed reaction. If you're not very familiar with computer programming, don't worry. This is just to show you that there's no magic going on in the background. I'm just using a computer to solve this system of differential equations. So to go quickly through the code, this first portion here is just loading necessary packages that will help me solve the differential equations and plot the output. This portion is actually defining our model, which has the four differential equations I've just discussed, describing the changes in these different species in an enzyme-catalyzed reaction. This is setting the constant parameter values to some constant. This is initializing the time over which we're solving the differential equations, because again these differential equations were all with respect to time, and setting the initial concentrations for each of my species in the model. This line is actually performing the solving process for the system of differential equations. We're using a function called odeint here, and that is what will do the computational work to solve the system. And then this portion here is plotting the output of the solution. So let's go ahead and just run this code. Over here you get an output, and here is the solution to our system of differential equations. It's a time course series of each of these different species, and you can see that this solution might have been hard to reach analytically, especially over this whole full time course. So here are our four equations once again, with the output we've just generated computationally, and clearly it's a very useful, a computer is a very useful tool to solve differential equations, and just bear in mind that most of the work we'll be doing, and that you'll be doing if you go into modelling in systems biology, will be computational work rather than handwritten analytical solutions to these differential equations. Now, in the computational method we've just explored, the differential equation solver, odeint, which we used in Python, was able to use numerical methods to reach an approximate solution to the system of differential equations. So numerical methods approximate the analytical solution, and the analytical solution is the exact solution to the system of differential equations, which is not always easily reached. Because numerical methods require many iterations to progressively approximate the solution, it is advantageous to use computational tools to arrive at a result, rather than to use these methods by hand. However, it is possible to do some of these methods by hand, and we'll explore one of the simplest methods now. The method we're going to look at is the Euler method, which approximates a solution by knowing the initial condition, which is the solution to the differential equation at a given initial time, and it also knows therefore the slope of this initial condition point, and it can progressively take steps in the direction of the curve to approximate the solution. In the Euler method, we must define a step direction, and this is given by the differential equation that describes how some species, in this case y, is changing in time. And so here you see the dy dt is representing that left-hand side of the differential equation that describes that process, and we've rewritten this as some function of time and concentration of that biochemical species y. And so if you go ahead and plot how the concentration of y is changing in time, the step direction is going to be essentially the slope at some point on that curve, or the tangent line to the curve at the specific time and concentration. Also, we must always specify an initial condition in order to compute the Euler method, and this is because we need to know where we're going to start stepping from on this curve, and then also the initial condition allows us to compute the first step direction that we take. So the initial condition tells us where to step from, and it allows us to compute how to go and take that first step. So the initial condition here is just given as T0, Y0, some initial time, and the concentration of our biochemical species at that given time. And finally, you must specify a step size in order to compute each of the steps in this method. You have the choice for the value of your step size. Smaller step sizes in general will provide a better approximation of the solution. However, it's much more computationally intensive, so there is some trade-off. But just to note that smaller step sizes produce smaller errors from the actual analytical solution. So the subsequent point on the curve can be computed using this equation, where a step is taken of step size h in the direction specified by the tangent line. This is a visual representation of what the Euler method might look like, where each of these intervals here are step size h. All of these have the same step size. The red curve is the exact solution to the differential equation, and these green lines are the tangent curves at each of the subsequent prediction points. The first point here at time 0 is known, and it's the initial condition. And from that initial condition, we're able to compute the first tangent line, and from there, each subsequent point is a predicted value that approximates the exact solution. So for example, here is the first prediction point. You can see there's some error here, which is the distance from the true exact solution curve. And each subsequent prediction must be computed using the same step size that we've specified and the tangent line that changes at each predicted point in order to approximate the exact solution. To illustrate how this works, let's go through one of the examples we've worked through in lesson 4, where we have dy dt equal to f of t comma y equal to 3 over y times t. And our initial condition will be the following. Y at t equal to 0 is equal to 1. The first step of the Euler solution is to compute the solution to f at our initial condition. So f of t naught, y naught, or f naught is equal to f of t naught y naught, which is equal to f of 0 and 1, which is our initial condition, equal to 3 over plug in 1 for y times 0 for t, which is equal to 0. The next step is to compute y1, which is our first predicted point, and y1 is equal to y0, which is plus our step size h times f0. For this example, let's say we have a step size h equal to 0.5. And this is then equal to plug in y0, which is 1 from our initial condition, plus our step size 0.5 times f0, which is 0, is equal to 1. So now we have f1 and we have y1. So then we once again are able to compute f1, and this is equal to f of t1 y1, and since t1 is defined by our step size, we've taken one step, so t1 is 0.5, and y1 we've just computed is 1. Now this is ultimately equal to, we plug them in, the values for t and y, and we get 3 over 1 times 0.5 is equal to 1.5 for f1. We then go about computing y2, and we get that's incorrect. And we get y2 is equal to y1 plus h times f1. So we've now computed y1 and f1, so we plug those in, and we get y2 is equal to 1 plus 0.5 times f1, which is 1.5. We get y2 is equal to 1.75. Let's do one more step just to continue to illustrate how this is done. Once again, y1 and y2 are the next two predicted points with a starting condition of y0. And this process can continue for as many iterations as you wish to compute, depending on what length of time course you wish to approximate. Now for one last iteration of this problem, we compute the slope at y2, which is f2 is equal to f of t2 y2, which is equal to, from before, 3 over 1.75 times 1 is equal to 1.714, and then y3 is therefore equal to y2, of course, plus the step size times the slope, f2, which is equal to 1.75 plus 0.5 as the step size times 1.714 that we've just found, and ultimately is equal to 2.607 for y3. Again, you can continue to compute these steps for as many iterations as you like. Euler is a very simple numerical method, and it's often not the most accurate or efficient, so other methods are commonly employed, but this is a good first step to understand how numerical methods work. In addition to the Euler method, if you are interested in looking up more numerical methods, the fourth order Runge-Kutta method is very common, and some other methods include the midpoint method, Hoynes method, or the backward Euler. And that concludes Lesson 6 in differential equations modeling and numerical methods. We've looked at a brief example of using a computer to solve a system of differential equations, which is very effective, and we know now that it uses numerical methods rather than analytical solutions to approximate the behavior of the dynamical system. These can be very computationally intensive, and so there are various numerical methods that we may use to get a better approximation for a given problem.